This is our first video on modern physics lessons, and if the previous topics, the subjects of the previous chapters that we covered in our videos were developed in 17th, 18th, or 19th centuries, the modern physics is the subject of the 20th century. It all started with the particle-like nature of light that was revealed and studied through the work of Max Planck in 1990s, beginning of 1990s, and later by Albert Einstein, who won the Nobel Prize in 1921, I believe. And it was related to his discovery of the law of photoelectric effect. When he published his studies, he stated that electromagnetic radiation is emitted or absorbed by the matter, and is emitted or absorbed by the individual boundaries called quanta, and a quantum of electromagnetic energy is known now as a photon. So the light behaves like a stream of photons, and this is illustrated by the photoelectric effect. So when the piece of metal is illuminated by electromagnetic radiation, specifically visible light or ultraviolet light or X-ray, the energy absorbed by the electrons near the surface of the metal can liberate free these electrons from the bound states of the metal, and these electrons can fly off and are called or known as photoelectrons. And in all the observed cases, they learned that the intensity of the light, the amount of light that will shine on the metal, does not increase the kinetic energy of the electrons that are being released. So the increased intensity of the light would not cause the electrons to leave the metal surface with a greater kinetic energy. And also the photoelectrons would not be emitted regardless of the frequency of the incident energy. So you cannot just increase intensity and get the higher speed electrons out of the surface. What you have to do is to change the frequency at which the photons are coming in contact with the surface of the metal, and by increasing the frequency or the energy of the photons, you can increase the kinetic energy of the electrons after they have been emitted from the surface. Hope you enjoyed the videos that have more conceptual understanding of modern physics. I'm going to jump into the practice questions because I don't want to waste these 30 minutes of your time. So there are a few formulas that you will have to know, and I'll start with the first ones. This one is going to be related to the Bohr's model of the atom. So in the years immediately followed by the Rutherford's announcement of the nuclear model of the atom, a young physicist, Niels Bohr, would add an important piece of the atomic puzzle. And Bohr's model of the atom explains the spectroscopist's observations using the simplest atom of hydrogen with only one electron. Bohr postulated that the electron would orbit the nucleus only in a certain discrete radii, and when the electron is one of these special orbits, it does not radiate or emit any energy. However, if the electron absorbs a certain amount of energy, it is changing to its state to excited state to a higher orbit, one of the greater radii. And after a short time in this excited state, it doesn't want to stay in excited state. It returns to the lower orbit, emitting a photon in the process. And these radii of positions where the electron is located called the energy levels, and the specific radius of the photon is emitted each jump that it has to go from the higher level to the lower level. So Bohr found that the energy of each excited state was the particular fraction of the energy of the ground state, and specifically the energy of the nth energy level of hydrogen is given by the formula. And this formula is, so if you want to find the energy of the nth level of the nth level of the electron when it's located in a certain level. So you have the nth level of energy, you have 1 over n squared, and then you have the energy of the ground level. And so the energy of the ground level, so right here you see it, the energy of the ground level is going to be equal to negative 13.6 for the hydrogen electron volts. So if n is the number of the level, so this would be the S sub 0, which is the ground level, and then each level is going to be having like S1 and then S2 and so on. So for the electron to go from ground level to a different level, you cannot, think about it like steps on when you walk on stairs. In order for you to go from this step to the next step, you have to bring your foot up a certain distance. If the photon that is coming to the electron does not have that energy to bring this electron from the ground state to the next step, then electron cannot jump. So it has to be a certain amount of energy in order for, and then I think this is a good example as well. So it has to be a certain amount of energy for the electron to jump from one state to another state, from one energy level to another energy level, and n is going to be that energy level that we're talking to. So the energy on a certain level is shown by this formula. This formula is for hydrogen atom, and then if you want to look at energy levels of other atoms, then you would have to add a Z number. So this would be a Z number, and this Z number is the number of the protons in the atom's nucleus. So when you have an element in the periodic table, it has the A number, the atomic mass number, and it has the Z number, number of protons in the atom nucleus. So when we covered electrostatics, remember that the voltage is equal to the work over the charge. So the work is the energy, so the work is equal to the energy, which is volt times the charge. And then this is where electron volt comes. So you have, instead of writing the energy, so this is your energy, right? So this is your energy. And instead of writing work, I'm just going to write energy. And that is equal to, instead of writing the charge of the electron, which is 1.610 to the negative 19 coulombs, I can write, and for each volt of energy, so potential difference. So if I can write 1 electron volt, and what that means, it is I have to replace the electron with, so instead of writing energy measured in joules, the work is measured in joules. 1 electron volt is 1.610 to the negative 19 joules. You will have to know these numbers to convert. Sometimes they ask the question to write the answer in electron volts, and sometimes in joules. So if you have 1 electron volt, you can write it in amount of joules. That would be this number. Also in AP Physics, I have seen questions related to this concept, and you have watched this in your conceptual videos that I posted for you, but in here I want to just mention that in all objects with a temperature above absolute 0 Kelvin, which is negative 273.15 degrees Celsius, emit energy in the form of electromagnetic radiation. And a black body is a theoretical or model body which absorbs all radiation falling on it, reflecting or transmitting none. It is a hypothetical object which is a perfect absorber and a perfect emitter of radiation over all wavelengths. And the spectral absorption of the thermal energy radiated by a blackbody depends only on its temperature. So here in the graph that you see that you have blackbody curves of several different temperatures, and they show different types of temperatures, and then the characteristics of the blackbody radiation can be described in terms of several laws. So there's like Planck's law and displacement law, or Stefan Boltzmann's law. And these blackbody radiation curves are quite complex shapes and can be described with Planck's law. For example, the temperature of a star can be detected from the wavelengths of the peak of its radiation curve. So it's used in astronomy when scientists study stars. So when we talk about the photons and the light, the nice way of it to think as a photon is the bundle of electromagnetic waves or energy. And the amount of energy that the bundle or the photon carries is directly related to the electromagnetic wave's frequency. So here is the energy of the photon that can be described by the formula. So the energy is equal to, and it can be measured either in electron volts that I mentioned earlier or in joules. So you have H, which is the Planck's constant, and that is equal to 663 10 to the negative 34 joules seconds, and then it times the frequency of the photon. The things here that you have to remember: the energy of the photon. So if we talk about the energy of the photon, it's going to be H, so it's more like the sign times frequency, so that's the Planck's constant, and that is equal to 663 10 to the negative 34 joules times seconds. If the energy is given in electron volts, you have to convert the joules into electron volts. So you could also rewrite Planck's constant in electron volts. That would be 414 10 to the negative 15. So 1 joule, 1.6, let's say this way. So 1 electron volt is equal to 1.67 10 to the negative 19 joules. So if you have 663 10 to the negative 34 joules, you have to convert this into electron volts. So that will be equal to, so I have x electron volts, so I'm looking for electron volts is equal to this, and 1 electron volt is equal to that. So I'm going to rewrite Planck's constant like this. I have x is equal to 663 10 to the negative 34 joules, and 1 electron is equal to this much. So how do I go from here to from this number to this number? I have to multiply it by 4.14 and 10 to the negative 15. So if you want to rewrite this number, Planck's constant, in electron volt, it would be 414 10 to the negative 15 electron volt times seconds. So this is a good formula to know. The formula for the energy of the photon, and also the Planck's constant, good to know. And then we also know from the waves that the velocity of the wave is equal to the lambda, the wavelength, times the frequency. And in when we talk about the photons, they don't have the mass, so they are just energy. They travel with the speed of light, which is 310 to the 8 meters per second. So I can rewrite c, the speed of light, is equal to lambda times the frequency. So I could replace the frequency of the photon as c, the speed of light, divided by the wavelength of that photon. Then the formula of the energy of the photon, instead of the Planck's constant times the frequency, it becomes the Planck's constant times c over lambda. So you can have used either of these formulas to calculate the energy of the photon. If the frequency is given, you use this formula right here, and then that formula. And if the wavelength is given, then you can use that formula by substituting the frequency with the speed of light over the wavelength. Another formula that we have to know in this section is another gift from Albert Einstein is his famous equation that is stating that E, again energy, is equal to mc squared. Here is the mass of the particle or the object, and this is the speed of light, 310 to the 8 meters per second. And it is a matter-shattering idea. It means that the energy of the mass are just two aspects of the same thing. So the mass is like a solid form of energy, and it can be converted into energy. So lots of energy, c squared, is a huge number, because 310 to the 8 is the speed of light, and then you square that, which makes a very large number. So you can convert the energy into the mass and create matter out of energy. So like these things always happen in all the time happen in nano world. And when we use the formula mc squared, we only looking at the rest energy of the object, but the total energy is different from the rest energy. So the total energy, you see the gamma factor appearing in front of mc squared. And that gamma factor has its own formula. So this would be the gamma factor formula. We don't have to use it in AP Physics 2. I'm just like mentioning so you know that that's not the full formula, that's just mc squared. And so the gamma factor includes the velocity. You see v over there, v over c squared. So you see v, and this velocity is the mass that has a velocity relative to an observer. So there are many aspects of the total energy that we do not need to discuss in AP Physics 2, but I just want you to know that there is more into this formula. So when you see E sub 0 is equal to mc squared, so right here you have E sub 0 is equal to mc squared. So that one is called the rest energy. So this is the correct form, that with gamma factor, of the famous equation of Albert Einstein. And the energy stored in the object is the rest energy, and it is also implies that the energy can be destroyed to release the energy, like the mass can be destroyed to release the energy. So you can convert mass into energy. So before we start solving problems involving some modern physics or quantum or photon related problems and photo effect, you have to understand the conceptual part. So I'm spending some time on making sure that additional conceptual understanding is there before we start solving problems. So before we begin the phase, make sure that you understand the experiment of the photoelectric effect, and it is really important, just the conceptual part. So this is the experiment that proves that light is a particle, even though we already know that it is a wave, because light has wave properties like interference that we studied earlier. And this is the experiment that opens up the wave-particle duality, the photoelectric effect. So when the light shines on the material, you can get electrons fly off the surface. And here you see some formulas that we're going to be using when we look at the photoelectric effect, cover some information here to use the area that is here to write down wherever I have to. So if you are looking for the energy again, so the energy is going to be equal to the charge times the voltage, or change of the potential difference. And this is when you get the electron volt or joules. So the energy can be measured in electron volts or joules. And then how do you know how much energy is going to be released? So when you have a photon, so if you have the photon has some frequency. I can see how much energy the photon has by using the formula H times F. You have Planck's constant times the frequency of that photon. And the photon hits the metal. So from here, if there is enough energy, an electron is going to be released. But some of the energy is going to be, so you have to rip off electron from the surface. And every metal has different work function. So sometimes you can see it as W, like right here, work function. Or you can see something like this. That can be a work function. So the energy that you have that is coming from the electron, so this is how much energy electron is going to be carrying, and that is equal to H times F. And that energy is going to be used to rip off the electron from the surface, and wherever energy is left is going to be the kinetic energy of the electron, the maximum kinetic energy. So this energy is going to be split into two parts of energy. One is used for the metal to rip off the electron from the surface, and the other one is wherever is left in the electron to fly from one surface to another. So like in this question, in this picture right here, you see the light is shining, so the photons are coming into the metal. So here is the metal, and ripping off the electrons, and then electrons can travel from one plate to another plate, and that creates the current in the circuit. So that's called photoelectric effect. What happens here when the electrons are released from the plate? They are released from the positive plate usually, and then they travel toward the negative plate. And when they this means that the voltage across the plates is acting as a stopping energy to stop the electron traveling from one side to another. And that voltage is called the stopping potential. And it is also can be calculated as the maximum kinetic energy of the electron. So if the electron have maximum kinetic energy, then that kinetic energy is going to be equal to the energy needed to stop the electron, or in other words, it is the stopping potential energy or stopping potential difference. Just to mention one more time that the intensity of the light does not increase the kinetic energy of the electrons emitted from the surface of the metal. What you need to do, you have to change the frequency of the photons that are coming, not the intensity of the light. So you see the red light has a lower frequency and the blue light has higher frequency. So in order to achieve the higher kinetic energy electrons, you have to increase the frequency, which is the blue light, compared to the red light. And the red light does not even emit electrons in the picture that you see, like 3 different plates. And then the red light does not emit electron. The green light emits electrons, but it emits not as high energy electrons as the blue light. The blue light has more kinetic energy electrons, like reflected or emitted from the surface. Actually see a problem here that I want to solve with you, and before the video is going to be over, I think I have to continue with more conceptual understanding or explanation in my future video, the second one. But I want to solve this problem over here. So they say that ultraviolet light with a frequency of 3.510 to the 15th hertz strikes the metal surface and ejects electrons that have maximum kinetic energy of 5.1 electron volt. What is the work function of in electron volts of this metal. So if I say that the kinetic energy of the electrons that are emitted, so maybe I'll move it this way. The kinetic energy is given of the electrons that are emitted. So kinetic energy is equal to 5.1 electron volts. So here you have the surface and the photons are coming. The frequency of the photons are given. So this is the frequency of the photons that are coming. And then the electrons being emitted out. And then the energy of these electrons, the kinetic energy of these electrons is given. And they ask you, so what is the work function of the metal? And when I say the work function, I mean the energy is used to rip off the electron from the surface. So I know that the kinetic, or let's say it this way, the energy of the photon is equal to h times the frequency, and then give me the frequency and the Planck constant I know. And that is equal to the work function plus the kinetic energy. So from here, I see that the kinetic energy of the electrons is equal to the frequency of the energy of the photon minus the work function, right? Or I can say that the work function is equal to the energy of the photon minus the kinetic energy of the electrons. So I can use this formula to calculate the work function. So I have the work function is equal to h. My energy is given in electron volts, so I have to use the Planck's constant in electron volts as well. Convert all of them into joules, but I don't want to. I'm just going to plug in my Planck's constant in electron volts. So instead of h, maybe I'll use this color. So instead of h, I have 4.14 10 to the negative 15. Then I have the frequency, which is 3.5 10 to the 15, and then I have to subtract the kinetic energy of the electrons, so that will be 5.1 electron volts. So everything is in electron volts right now. So the work function is equal to, I get 9.4 electron volts. So that is the energy that is needed to rip off the electron from the surface of the metal. And if I wanted to calculate how much energy the photons had, so I would multiply these guys together, and that would give me the energy that the photons is carried. This is the energy that is left for the kinetic energy, and this is the energy that was needed to pull out the electron from the surface. I'm running out of time in this video, so I'm gonna finish this video, and I'm gonna continue with more practice in the following video, and there's more conceptual part that I have to talk about. Thank you for watching this video, and I will see you in the next modern physics, quantum physics introduction video. Thank you.